Vitreoretinal surgery, which is the surgical domain we are interested in terms of a clinical application, is very mature. Our collaborators at Moorfields Eye Hospital, for example, Lyndon Da Cruz, is extremely skilled at doing conventional surgeries. But what surgeons cannot do is they cannot access parts of the human eye within the retina in order to be prepared for the upcoming regenerative therapies that will appear. So the retina of the human eye is as thick as the human hair. And ultimately, these therapies would need to be deployed inside that hair-thin structure, so at the specific layers of the retina. And that cannot be done by the human hand, and it cannot be done by the human eye. So we are developing technology to improve surgical dexterity and improve surgical perception and cognition. So today what we will see and what we will talk about is some of the recent developments we have made in the field of surgical robots, specifically microsurgical robots for regenerative therapy delivery in the eye and other parts of the human body. We call it Viper. Viper is a good name and a bad name. It's a good name because it's a snake, and what we have is a snake-like robot, so it has this flexibility. It's a bad name because it's a venomous snake, but what can you do? But cool is it actually stands for something. It stands for Versatile Intraocular Precision Enhancing Robot. And this is exactly what our device is doing. It goes inside the eye and increases the performance and the dexterity of the human surgeon. So what we have here is the instrument that we are ultimately making. And so this is a geared system that will be deployed on an actuation system, which is what we have here. And it will be deployed on an actuation system, and then inside here we are housing small elements, and depending on how I move these elements in and out, then what is happening is that I'm able to control the extension of the tool, and depending on how I rotate them, I can control the curvature of my instrument. And so ultimately this thin bit here at the tip is what's going to enter the patient's eye, and depending on how I reorient and I control these flexible tubes, I will be able to offer the surgeon dexterity as if they had their hand inside the eye. So they could delaminate any way they want, they could do an injection any way they want. You need something to hold this, which is still not that heavy, but you also need to take this into position. And so that's hence the robotic arm.
What we have is a standard microscope foot pedal, so the microscope that's in there, and we've taken this and changed it to do our own stuff. So for example, if I press this, it activates the hand guidance of this robot. So say that there's a head here, so you essentially just take it, you bring it down to the eye, and then surgery happens, blah blah blah. The surgeon will actually use this part of the foot pedal to control how we actually move the tip at the end, and then whenever we're done the finish, you just press this button again and you bring it out.
So a lot of the algorithms that we're trying to make have to do with like how do you make these motions smoother, because this is a big robot actually, it's very heavy. And to be able to move it like this in a semi-transparent fashion is, has a lot of other problems to solve under the hood. We started working on this project in 2014. I was supervising a student when I was a postdoc myself, and we created with Hobby Electronics a very crude version of the system, showing, okay, can we make something that has this sort of functionality? Since then, we have attracted grants and charitable donations, and taken this to the development of, better controllers, optimizing how the tube should be, securing IP, and now working with a quality management team and a manufacturing facility in-house to understand, okay, what do I need to do in order to satisfy a risk reduction for this sort of devices. So it's been a journey of around 9 years. There is a clear roadmap on taking this device to not only first in human, but really clinical practice. And we are investigating the elements that we need to have in place in order to achieve that. We are very close to creating a technical file, which is what the MHRA requires in order to give you permission for first in human. We hope to have this ready within a year to a year and a half, and then proceed to a first-in-human evaluation of a simpler concept of our system within, let's say, 2 to 2.5 years. So really, it is within reach, and we are eager to take it all the way. So we will do a lot of tests like this. We use the plastic eyes, and so you go to a stage where you're kind of confident that this will work, and also, well, that's what the MHRA wants to see as well. that you are confident that this will work, and you have the data, the evidence, and then you convince them. The operating room of the future will be an environment where artificial intelligence agents, robotic agents, and human agents work collaboratively to improve healthcare delivery. You can imagine that you will have like a sensorized operating room with cameras mounted on the ceiling and sensors on the instrument, and some sort of like 5G or 6G protocol where all these machines, through something what we call the Internet of Medical Things, communicate with each other, share data, and then the artificial intelligence, supports surgical decision making. The robot offers autonomous or semi-autonomous assistance or dexterity assistance, but you around that have like an optimization of workflows. Like, how do you make sure that the human actors also work in an optimal fashion? How do you make sure they're not idle? Because you could share resources even within operating rooms if you make sure that, okay, you are not needed in that room. Why don't you go and like take care of something in the other operating room? And imagine this as like a thing that has like a brain, and we are all as actors, humans, artificial intelligence, and robots working in this sort of like environment. So it's exciting to be at the frontier of medical progress, because first of all, you keep your ears open about all the new stuff from the medical and life sciences frontier. So like if I wasn't in that domain, I wouldn't know about stem cells, gene therapies, upcoming therapies, clinical trials. So that's a very, very exciting. You don't have your foot in that other world, but you kind of like osmotically gathering information. This is very exciting. On the medical technology side, what is extremely exciting to me is to see something that we started developing in 2015 with hobby electronics, like that worked or not worked, and then how you are able to take it as much as you can to something that is ultimately reaching the patients. And the interesting thing is that in this sort of translational pathway, the more you dig, the more questions you uncover, and things that are dismissed like, that's easy, like I will just do that. There is no just in research. Like everything ends up being more complicated and requires much more digging and research, and eventually this becomes like a very nice body of work that you see that you've taken from a very low starting point to something that the leap to the patient, like in the imagination, is not that big.